Okay, so as promised in the previous class, let us start discussing about PLL, which is called phase lock loop. Okay, this is a typical circuit which will be mostly in many places will be used in communication. So it has utilization in digital communication as well, because there also you need to do clock recovery. For clock recovery, PLL is one of the integral part. For the topic we are discussing, this PLL, that's where it is very important, that carrier recovery. You have already seen that if I wish to do coherent detection or coherent demodulation, where I need to generate a local carrier, we have already seen the effect of that local carrier drift. So we need to have something where the carrier is properly synchronized and locked to the incoming carrier, okay, with respect to frequency and phase. Okay. And you will later on you will also see that this particular circuitry is also being employed heavily for FM demodulation. So we'll once we understand the mathematics of or the basic principle of this circuit, then we'll discuss about frequency modulation, and we'll see that how this can be very easily used for FM demodulation. So this is one of the circuit for communication, probably one of the most important circuit. So let us try to discuss about it. It's essentially means we are saying phase lock, that means we are trying to lock the phase. Okay. So whether it's frequency or phase, so suppose I have a cosinusoidal, let's say A cos omega c t plus some input phase it is having, right. It might be time varying, it might not be, even omega c might be time varying, might not be time varying, whatever it is. Okay. So we are saying that this is the phase and this is the frequency, or overall we can say this is actually the time varying overall phase of that cosinusoidal. Okay. So this is the phase and we want to lock this overall phase, that is our target. Okay. Within this there are two constituent part, one is the frequency, another one is the phase. Okay. So pure phase probably. And generally what happens, if I have the representation like this, where omega c and theta are non-time varying, that means they are constant with respect to time, then that separation of frequency and phase comes into picture. Okay. Otherwise it's the overall phase, because once both of them are varying with time, I cannot really discriminate what is frequency and what is phase. Whereas if this is the way it's happening, then I know that there is one part which is multiplied by t, so that's my frequency, plus there is some constant part, that's the phase. Okay. So that is how we give a definition of frequency and phase, we separate them, extract them out. Otherwise in a completely time varying scenario where omega c and theta are also variables of time, I cannot really discriminate between them, it's just overall phase of that cosinusoidal, okay, which is time varying. So and that is why this particular circuitry is called phase lock loop. That means whatever this entire phase is, I want to lock it to that. Okay. It might vary with time, but my things also should have equivalent variation. Whatever I will be generating at my local oscillator, that must have equivalent variation. So this is what I want to do. So definitely if I wish to lock something, immediately one thing comes into anybody's mind, that's feedback loop. So that is why it is called also a loop circuit. Okay. So we will have a feedback, and with that feedback we will try to actually minimize the phase error between the incoming and the outgoing. So that is the overall principle. The principle is very simple. I will have a phase which is incoming. So let us say I will have a cosinusoidal which is coming with a incoming phase of theta I t, and locally I will be generating some phase theta o t, and my target should be that this difference theta o to theta I or theta I to theta o must go to 0. So I need to create a feedback loop so that that error, which is the phase error, must go to 0. That can only happen with a feedback if I try to do that. So my circuitry also will look like that, it is a feedback circuit. So, the circuit is something like this. It means before drawing the circuit we should talk about what are the things it consists of. One, it consists of a VCO, this is probably the first time you are hearing, that is called voltage controlled oscillator. This is a typical circuitry where you actually give a input voltage, and proportional to that voltage it will, this is an oscillator, that is why it is called voltage controlled oscillator. So, it will create a oscillation, but the frequency of oscillation, so it will actually create a sinusoidal wave, but the frequency of oscillation, which is that omega c, must be proportional to the input voltage that you are giving. Okay, so that is called VCO, voltage control oscillator. That means it is a typical circuitry where you can give an input voltage and you can expect that outside or output will be getting a sinusoidal which has a frequency which is proportional to the input voltage. Okay. So, typically we write it like this. So, the omega c t, okay, which is the frequency of oscillation of this voltage controlled oscillator. So, this is the output. Okay. Output is actually, I should say, it is a cos omega c t or omega t. Okay. So, it is a cosinusoidal which has an instantaneous frequency of this one, and this must be some omega c constant, I will talk about that, plus some constant into E0 t, where E0 t is the input of the VCO. It gives me some, I can take A cos omega t, right, where omega t is this. Okay. So, you can immediately see that omega t, that is the frequency of that cosinusoidal which is coming out of VCO, that is proportional to E0 t, but there are, proportional means it must be linear. So, this is a linear curve with two constant which are specific parameter to the VCO. One is this omega c. What is omega c? That means if I actually do not give any voltage as input, and if I keep the VCO to run freely, that means I give power, VCO is operating. So, if I keep him to run freely, then this is the frequency at which he will be running. Okay. So, this is the output frequency he will be generating, that is why it is called free running frequency. Okay. So, that is a typical parameter to a VCO. Different VCO can have different standard and different free running frequency. So, accordingly you will be buying a VCO with your targeted carrier range, right. It should be around that, your free running frequency should be around that. So, that is the omega c. Okay. And c is just a constant which is by which the Et is multiplied. So, that is probably that slope of that linear variation. So, that is also typical to a particular VCO. Okay. So, these two parameters will be given for a chosen VCO. So, what will happen if I have some some E0 t input to it, it will keep on running at different frequency. Now, if I put the VCO in a loop circuit, remember my target is this E0 t, if that is the error voltage, let us say, or that is equivalent to the error phase difference, then I will be targeting that error must be 0, okay, in the loop. That is how I will be designing the loop, you will see that later on. But remember, if I put it in a feedback loop, then this error will be 0, because the error will be generated by a phase difference between the input phase and output phase. So, that can only be 0 if these two frequencies are locked. That means it will not be, when the error is 0, VCO will not be in a loop configuration, VCO will not be operating at omega c, because the input error is 0. In a loop it will actually run at the frequency which is equivalent to the incoming frequency and phase. So, this is something you have to always consider. Once I write this equation, you will be always thinking that as if I put E0 t equal to 0, it will be always running at omega c, but that is not the case. It is the case if I am not putting it inside the loop. It will not be the case if I put it inside the loop, because inside the loop it will actually run at the frequency which is completely asynchronous with the incoming phase and frequency, because then only the difference will be 0 and the VCO will not change further. So, it will be locked to that. So, we will see that. Okay. So, I can see this. Now, let us say the VCO output. So, the VCO, if it is running at this frequency, so what should we get? Let us say VCO output is, according to my target, is some B cos omega c t plus theta output t. Okay. So, this is my target. I want a VCO which must run with this frequency and phase. Okay. But what is happening? If the VCO input is E0 t, then that must be the omega t. Okay. Fine. So, from here, this is the phase. So, what should be the instantaneous frequency? I should differentiate it, because when this phase term was constant, it was omega c t plus some theta. If I differentiate, I get the frequency. So, for instantaneous frequency from the instantaneous phase, it is always the differentiation of it. So, that must be omega c plus the first derivative of theta o t. So, this must be the VCO instantaneous frequency, whereas I have already said that this must be the VCO instantaneous frequency, that omega t, okay, if I give E0 t as input signal. So, this two must be same if I put that VCO inside. So, therefore, I can always write that theta output t differentiation must be equal to this inside the loop. Okay. When I put the VCO inside, VCO output will be this, that is my output phase, and I assume that it is running at omega c. Okay. So, if that is the case, this output correspondingly I will be having a instantaneous frequency. So, I calculate that, and I have also told that VCO instantaneous frequency must be this. So, therefore, there must be a relationship between the output phase as well as the input voltage. So, that is the relationship we were targeting, and we have got this. Okay. Now, let us see how do we use the VCO for PLL. So, it is like this. I will have a signal which is A sin omega c t plus theta I t, which is coming. Okay. Remember this is the carrier I am getting. You might be asking, okay, where do I get this carrier? Okay, that is the first question, because the PLL, if this is the PLL we are designing, so PLL will be at the receiver circuit, I do not have the carrier. So, we have already talked about that squaring and narrow band pass filter, passing it through that we get the carrier with some phase, whatever carrier phase has, carrier frequency or carrier phase, this is that. So, basically before PLL always you will be employing that squaring circuit, and for SSB and VSB we have told that PLL cannot even work because that squaring does not give me carrier. So, if I do not get a carrier over here, pure carrier over here, VCO cannot help. Okay. So, it is very important that after squaring and putting a narrow band pass filter, I must get a carrier. Okay. If I am getting that, then I can employ the VCO technique. So, VCO will take this carrier, whatever it is, with a phase and frequency, then he will have a multiplier circuit. Okay. So, in that multiplier, what he is doing is giving the output from VCO. Okay. So, VCO will generate, as we have already discussed, that it should be generating B cos omega c t plus theta output t, right. So, that is the signal VCO is generating, we have already told that. Okay. So, if the output phase is theta, we will have a multiplier circuit followed by a low pass nature of loop filter. With a transfer function of Hs, whatever it is a low pass filter. We will see why low pass filter is required, and that should produce the error signal which should be fed back, because it is a feedback circuit, to the VCO. Okay. So, this is all we are doing. Let us try to see if this is correct. Okay. This is what we are targeting. So, what is happening whenever we multiply, what do we get? We will be getting a multiplication of these two. So, that should be so I have this and I have this. So, if I multiply, I will be getting after multiplication. So, it should be A into B sin omega c t plus theta I t, right. That is the incoming signal with incoming phase, and then the VCO generated one. Very carefully check, I have already assumed that probably the frequencies are same. Okay. That is not a requirement, will just after some times will prove that that is not a requirement. Okay. We can always have any frequency that the VCO is running at, or any input frequency which is different from the VCO free running frequency, we can still track it. We will prove that. But right now we are probably assuming that probably the frequency is already synchronized, it is the phase I want to track. Okay. So, if that is the case, so I will multiply these two. Okay. So, after multiplication it is just half a b. So, we will have 2 sin a cos b. So, I can just means put sin a plus b and a minus b, that formula. Okay. So, we will be getting sin this minus this. So, that should be omega c t will be cancelled. So, I will get theta I t minus theta o t, right, and then plus sin, I will have this plus this. So, that should be 2 omega c t plus theta I t plus theta o t, right. I will have these two terms. Now, you can see after the multiplier, this is where I will be getting these two. I want at this point just the phase difference term. So, I do not want this. What is the procedure to reject that? Just a low pass filter. So, that is why this must be a low pass filter. This will reject this part if it is designed properly, so that 2 omega c t term it cancels out. Okay. So, immediately at this point I will be getting just the sine, this difference, phase difference, pass through the filter transfer function. Okay. So, let us say the filter transfer function is Hs, and corresponding, if I do inverse transform, the corresponding impulse response is Ht. So, what should I expect at the output of the filter? That must be convolution with this one of that sine signal. So, it must be my E0 t, which is generated as error, that must be equals to that Ht, that is the filter means impulse response convolution with whatever signal I have got, half a b sin theta I t minus theta o t, right. Because I know the filter is already a high pass low pass filter, I have neglected the other term because that is not required. So, this must be my overall output E0 t. E0 t I can write that as, means I can multiply this by c. So, I multiply by c. What was c E0 t? That was actually theta o t differentiation. So, I get this equation, c, of course a b half comes out, integration minus infinity to t. So, I am just writing that h t convolution this. So, that should be h t minus x sin theta I x minus theta o x. So, I have just put the convolution. Okay. Where I will be now putting this half c b, that is a term completely defined by the VCO, because c is also a term of VCO and it generates an amplitude of b. So, these are all terminal, means these are all parameter of VCO. So therefore half CB I can just represent as a parameter of VCO. So I can write that as K. So I can have then A K and integration this term, right, where this I can write now as theta E T or AX, fine. So far I have done this. Now let us try to see if I can get a equivalent circuit of this one, okay. So the equivalent circuit now I wish to define is, see earlier what I was having a cosinusoidal. If I just put that circuit, this was the actual circuit of VCO. I was putting two cosinusoidal, I was putting a multiplier. The circuit immediately becomes a nonlinear circuit, right. I have no way to actually analyze it through linear circuitry, okay, or linear circuit theory method. So from there I wish to now transform this to a linear circuit, right. So what I do, instead of taking this sinusoidal and cosinusoidal, I take it from the phase perspective, as if my input is phase, output is phase only, okay. So what I do is I transform this circuit as if I am giving a input of theta I t, okay. Instead of giving that sinusoidal, I can just think about that I am the sinusoidal, all other parameters are fixed only, okay. So that has nothing to do with the circuitry, A and omega c, those are not going to change. It is just this phase which will be actually tracked and controlled, okay. So this phase has to be properly designed. So what I can say is, this is the phase which is coming in, and then after that I can put a adder circuit. So this is where the multiplier becomes adder, because if I see it from phase terminology, it is just phase addition or subtraction, okay. So what has happened inside, if you see, I have a sinusoidal and I have a phase subtraction. So this subtraction part only I will pick. So what I will say that I have an output phase which is being generated from the VCO, okay. So VCO I will put equivalent circuitry, okay, later on, but this is the phase that is being generated. I will put plus here, minus here. So that should be the theta E t. But what I have got inside before the loop filter is sine of that, right. So I pass through a sine converter. So this will just take that phase and convert it into sine. Then I get exactly what should be the input of that loop filter. Then I put this Hs, but in that Hs now I should also have something which is, if I have just done sine this, then sorry, not this part, if I just convoluted sine with this one, this particular term should be part of it. So what I can do now, in Hs I can include that, that is a constant term. So I can just put, instead of Hs I can put A K Hs, fine. Then this sine will just convert it to sine theta I minus theta O, then AK will be multiplied, because either it is in the signal or filter, it does not matter, because this is a constant term. Hs is automatically there, whatever I get over here, that I can term as my C E0 t, right. So that I can term as C E0 t. So if this is C E0 t, because that is what we have told, that is the error signal. So this, after convolution I get the error signal C E0 t. So if this is C E0 t, then what should be the output? That is just the differentiation of the, so this must be theta dash. So what should be this circuit then? This is the integrator, that is the beauty of it. So you can immediately see very nicely that nonlinear circuit, if I just visualize it from the phase perspective, I can actually transform it into a linear circuit. I have an adder, I have an integrator. In S domain this will be also treated as a linear part. Hs is a realistic filter, so no problem in all these things. Only problematic thing is this sinusoidal. So we will now, means in the next class probably we will try to see how to get rid of this. What we will say, a very simple assumption will get rid of this. We will say we are doing a small error analysis. That means the VCO has already almost tracked it, or generally if I have a carrier signal, I will actually give a input which is very close to the carrier, because it cannot be that I have a carrier coming at 5 megahertz and I am just starting from 1 megahertz. I will never do that, because I know roughly it is 5 megahertz. So, the VCO that I will be putting, free running frequency will be already around 5 megahertz. It is just that small error that needs to be tracked. So, if that is the case, the phase error should be very small. So, I can say this theta et is very close to 0. If that is the case, what can I write about sin theta et? That must be almost equal to theta et. That is it, I do not need this. And immediately I can say that entire circuit becomes just a linear circuit, and I can just do the equivalent transfer function calculation and the whole analysis, whether I will be getting a means whether this particular thing should give me a tracking and what kind of tracking it will be, can it track phase, can it track frequency, and all those things. So, in the next class what we will try to do, we will do this small signal analysis or small error analysis and try to see what kind of tracking is required. Only thing that is in my hand, VCO, it is an integrator, I cannot touch that. All those constant I can change, but that will not change the overall transfer function of the overall circuitry. The only thing that is in my hand is the filter transfer function HS. So, we will see what kind of filter to be employed and correspondingly what kind of tracking I get in terms of frequency and phase. So, in the next class we will discuss that. Thank you.